by listing out all of this stuff, I'm basically giving you all the different keywords that you could see within a problem to indicate that it's a chi-square situation. Not the least of which is the fact that, I'll show you on the next page, it's going to be represented as a two-way table. So it's going to stick out like a sore thumb anyway. All right. Now, you could see all of this stuff here is pretty intense. I mean, look at this, the notation and calculations and all that stuff. Everything I put in bold italics here, I didn't note it anywhere, but anything in bold italics is stuff that you would do if you, for some reason, opted to do this all by hand. All right. So, by all means, if you wish to explore that sort of thing, you're welcome to do that. But really, it's coming down to the same structure as everything else that we've been doing. Null and alternative hypotheses, alpha values, p-value, and a conclusion. All right, the conclusion here is following a similar template, very, very straightforward. The only difference is that we're using something called a chi-square test. You might look at that as an X. That's the Greek letter chi. Right? So it's different, but similar enough that people get the idea confused. All right. So it's kind of strange because you're gonna see like chi-square values in your calculator and be like, oh, is that x squared equals? Do I solve for x? No, you don't do that. But it's irrelevant anyway because we only need the p-value. All right. So what we're looking for here is an association between variables. All right. What we talked about in the probability unit was the concept of dependence and independence. Right. Probability, I mean, we scratched the surface of probability. There's entire courses related to probability. And I think we all got the sense of that as we were going through it, that there was a lot more to this thing than what we were looking at. And this is one of those aspects. All right, but this is kind of like a roundabout way of determining independence and dependence without having to get into computing individual probabilities. The calculator will handle it all for us. But fortunately, we're familiar with the calculator. We've been working with it all semester. All right, so when it says test the claim of no association, that's a statement between that's a statement of the null hypothesis. All right, so all I'd have to do is make a statement saying for HO that there is no association and we could streamline it between pass fail and the course 2A versus 2. This is actually a real data analysis I did back when I was first starting to teach. I was teaching two math courses on a high school level. One was called Math 2A and one was called Math 2. The Math 2A was a designation for a below grade level course. You know, some schools call them remedial, some call it extended. Most schools try to come up with a way to designate that course without using. They try to be very politically correct about it. Yeah, something like that, without saying designating it as something that is less than the standard level, right? But it's less than standard level. You know, it's at a slower pace. Our extended math in the high school that I teach, Math 2 extended is you get a double period every other day. So yeah, you're covering the same content over the course of a year, but you have to take half as many, again, math periods over the course of the year. So instead of 180 days, you have 270 days of math throughout the year to cover the same content. So it's pretty clear and obvious that it's a different course, right? But what I was looking for is whether or not there was some relationship between whether you're in one course or another and whether you are likely to pass or fail, right? Because in theory, you would think that these numbers would not look like this. Like as a teacher, this is alarming. All right, for the 2A students, I'm looking at this. You have the lab period, the extra lab period every other day. So the extra practice period to do more work in class, more hands-on collaboration, things like that. And yet, in this one class of 16 students, the majority were still failing. And it's like, well, that shouldn't be the case. I'm not saying it should be like it was in 2, where almost everybody's passing. I don't know what it should have been. I just know it shouldn't have been that. All right. So what I was studying was to see whether or not there was any kind of association between just being in that class and whether you were likely to pass or fail. All right. So the alternative to no association would be that there's some association. All right. In the interest of avoiding writer's cramp for all, we just say some association ... and this is the standard abbreviation. All right, because we know now what the some association is related to. It has to be some association between pass fail and 2A2. Yeah. Yep. All right. So we have a contingency table or a 2A table just like we had in the probability unit. And all we would need to do is pop these values into what's known as a matrix in our calculators. All right. And I'm going to show you how to do that. And the benefit of learning this new skill is that we will have the ability to type this information into our calculators and have a stat test evaluate everything for us. All right. So back to the calculators. Oh, alpha value is 0.05. So the next time we come up for error here from the calculator, we'll have a p-value, we'll draw our conclusion, and that'll be it. All right. That's the beauty of this type of approach, is that you're writing the null and alternative, and really if you think about it for all the other hypothesis tests, that's what you're doing too. Null and alternative hypotheses, take note of what the alpha value is, you go for the deep dive in the calculator, next time you come up for error you have the p-value, and you draw your conclusion, and that's it. All right. So this is the first time we're doing a process that does not involve the stat editor, which is somewhat different. All right. So what we're going to do is hit second and then this inverse key here, this x-1 key, and let me do an actual screenshot of that. A little keypad action here. Oh, fortunately, it's so large. I was hoping for that. Spend the next 20 minutes resizing it. All right, so let me highlight. I'll use Creative Pen here. No, I'll use highlighter. Let's not get too crazy. You're hitting second, and then you're hitting this x-1 key. All right, it's a brand new key for us, so it's worth taking the time, because it's going to bring us into a matrix editor. You're going to right arrow over to edit and hit enter. Now, you got to be careful about this because the column in edit looks just like the column for names. So it's very easy to be in the wrong column and not know it. You see, column for names and column for edit look exactly the same. All right, so just be very careful about that. And so just make sure you're in edit. What we want to do is type in the dimensions. The squeaking is killing me. We want to type in the dimensions of our matrix. So our matrix has 2 rows and 2 columns. We could tell that by the table that we're given. All right, we don't include the totals. So 2 rows, 2 columns. So number of rows is 2. I'll just write number symbol in front. hashtag column, no. Number of rows, number of columns. 2 in both cases. Sloppy handwriting, but hopefully it gets the idea across. All right. So when it says matrix A, 1 by 1, I want that to be 2 by 2. So 2, enter, 2, enter. And it reforms the matrix to the appropriate size. All right. So then I'm going to type in the values, 7, 19, 9, and 3. All right, left to right, top to bottom. So 7, enter, 19, enter, 9, enter, 3, enter. All right, enter after each value, just like you would if you were putting it in a list. All right, so then after that, we can actually get out of the matrix by hitting second mode.
On the bottom you have different numbers, but my calculator shows 2 comma 2 equals 3.
2 comma 2 equals 3 is what I have. Row 2, column 2 for matrix A is entry 3. Yeah, it's the same. So we quit out of here. And now what we're going to do is hit stat test. And you're looking for the one that says chi-square. All right. So we're going all the way down in the bottom. So I just hit the up arrow. So that brings me to the bottom. And then I just find the one that says chi-square. So there's 2 types in most of our calculators. There's 2 types of chi-square. There's chi-square and chi-square GOF test. We're not going to do the GOF test. We're just doing the chi-square test. All right. All right. So hit enter on that one. And it brings you into this menu where it says observed and expected. And it has 2 matrices identified. All right, matrices, plural of matrix. Let me get rid of this. Get a cleaner one. That's not a cleaner one. That's a cleaner one. All right, and you might think, wait a minute. We didn't put anything in matrix B. But it very clearly right there says expected B. And before I knew how to effectively use this, we would actually have to put values into matrix B. We'd have to do some math, all those calculations that we skipped over on the previous page, the bold italics. I said you don't have to worry about it unless you do it by hand. I incorrectly made all my students do it by hand because that's all we had to. Don't mess with this at all. Is really the moral of the story here, because the calculator is going to compute the values, the expected values for you, and plug those into matrix B. All right. We put values in matrix A. The calculator for us will put values in matrix B. All right, and then calculate for us. All right. It does all that on the fly. We'll take a look in a few minutes at what those values are, but we just need the P value. All right. So I'm going to go to calculate here, hit enter, and I get this information. And again, like I said, you do a lot of work in the calculator. Next time you come up for air, you have a p-value. I keep going with the wrong one. Undo. All right. So this p-value is less than the alpha value, so we're going to reject the null hypothesis. All right, so the null hypothesis is no good. The alternative hypothesis is true, which makes sense based off of the data. I mean, statistics, it generally asks more questions than it answers. I don't know why. I didn't know why. I still don't know why. Was it attendance issues? Partly. Was it behavior? Yeah, probably. Was it they weren't really trying? Okay. Did they do any work outside out of the classroom? I have no idea. All right, that's the lurking variable that always comes into play as a teacher. What are the students doing when they leave the classroom? Because I know exactly what they're doing when they're in the classroom. And you can infer some things and sometimes incorrectly judge students based on their mannerisms and behavior in class. I just this past week incorrectly judged a student because in the high school because they didn't seem like they were really doing anything in class. Apparently they have focusing issues and things like that, diagnosed. But I'm not an expert on that stuff, but their better time for learning math is at home in a quiet environment. So what they do is they do the best they can throughout the school day, and then they go home and they hit the books hard, and then they come back and they test and they ace it. And I'm like, yeah, you really got to step it up. You got to get it done. Otherwise, I don't know what's going to happen. And then they come in and they show me. They're like, prove me wrong. They did. 100 on the test. I'm like, whoa, all right. So because I don't know what you're doing outside of the classroom. Not doing much in the classroom. So logically, the assumption is, well, if you're not doing anything in the classroom, what are you doing outside the classroom? Maybe nothing, maybe everything, So I don't know. There are a lot of variables that come into play. But what this conclusion is telling me is that it's worth looking at. All right. If I got a fail to reject the null hypothesis, then I would have stopped the investigation. I'd be like, okay, the probabilities are saying, well, this could be a distribution that occurs in nature. Like just by a roll of a die, this is pretty much how it could have played out. So maybe if I had another sample of 16 2As and 22 math 2s, it could have gone the other way around, where most of the math 2s were failing, and most of the math 2As were passing. That would have indicated if I did not reject the null hypothesis, it would have occurred that this distribution of data could have occurred just by the roll of a die. All right, which would have meant that there was no effect, no relationship between those two variables. But because there is something going on here, it's worth the investigation. Right? And an investigation happened, and still didn't draw any meaningful conclusions. But at least you know to look. Right? Now you could look at this, and you could decide what are your two variables. Like this is a classic instance of bias. Any kind of situation where you think bias might be at work, you could run a chi-square test and make a determination, right? Because whether you're talking gender, whether you're talking age groups, whether you're talking about political groups, ethnic groups, whatever, and some sort of issue, it starts the conversation. You cannot, when it comes to stuff like this, make a law based off of the outcome. You can't say, well, the data says this, and therefore, well, we better change policy. No, that's the beginning of the conversation, but this stuff tells us that a conversation needs to happen. All right, so that's probably one of the most important types of hypothesis tests. All right, so anyway, we'll write the conclusion in a second, but let's go back into the matrix real quick, and let me show you what the expected value should have been. All right, so we'll go into second inverse, so the same keystrokes. Second, that x negative 1 key. And now you can see that both matrix A and B are labeled with 2 by 2. And you might have that thought, oh, wait a minute. I only put information in matrix A. Where did that come from in matrix B? The calculator did it for us. So we're in names. What we're going to do is select matrix B now and hit enter. That brings it into the home screen. All right. So right into the home screen, you'll see just that B in a bracket. When you hit enter, it'll tell you what the entries were in that matrix B that the calculator used for the chi-square test. All right. So what this is telling us is based off of the total number of individuals within each group. So I'll come back to that in a sec. But the total number of people who passed and total number of people who failed, total 2A students, total 2 students, this is what the breakdown should have been. Should have had around 11 people who passed for Math 2A, about 5 people who failed, about 15 who passed, and about 7 who failed for the other class. All right, so if things were equitable, that's what the breakdown should have been. Well, that's going to be part of your final answer. So what we're going to do, and that's the reason why I left space underneath the cells in the matrix up here, is what I want you to do is put the approximate values, the rounded values, because I don't want you to put the whole decimal in there. Put the approximate values of the expected values below the observed values. Right, so we're going to write about 11. You could use the approximate symbol or not. I like putting the approximate because I think it makes it clear that it's a rounded value. So it's a useful device, but if you just wrote 11 and 15, that's fine too. I'm not going to lose sleep over that kind of thing. All right, so that's what they should have been. So we want to have those numbers in there for 2 reasons. One, so that I can give you partial credit if you screw this up. Because really, I mean, you see a lot of stuff on this screen, right? Look at all this. Yeah, none of that's getting written down when you take the test. You're going to write down the null, alternative, what the p-value is, whether you're going to reject, and the conclusion. But if you screw something up, I don't know where you went wrong. If you give me the expected values and they're incorrect, I know where you went wrong. You typed the data in incorrectly. All right. So that it gives me the ability to take off 1 point as opposed to taking off like 4 or 5 points. All right. So we want to have them there for that reason. The other reason is, like, I try to come up with what I think are not clever but relevant problems, even on tests, things that you could even possibly learn from. So when you look at a problem like this, I do want you to have that, oh, that's what it should have been moment, right? And it's easier to see that if the numbers are stacked. 7 should have been 11, 9 should have been 5. Oh, that's what the breakdown should have been, this is what it was. It's very easy to see now that these original numbers were way off from what they should have been. All right, you should have had, in both cases, majority of students passing, but in this case, we have overwhelming majority of students passing, well, not overwhelming, but just a simple majority of students failing, right? So now you might look at this and say, well, is this just a dumping ground for students who aren't trying in this class? You know, because in a lot of cases, that's what it ends up being, you know. Like, we try not to make that be the case, but sometimes that's what the powers that be make that kind of environment, you know. So, oh, you're not trying. Oh, yeah, go into the lower level class. You have the ability, you know. Last year, I taught a freshman level math class. I had 3 students that wanted to drop down to the lower level. I refused to let them go because the guidance counselor said, do you think that they would be better off in the lower level? And I said, these are my words, I said this to the parent too, I have not seen them try yet. Until I see them try, I don't know if they have the ability. So until I see effort from them, I cannot make a determination of whether or not they have the ability to be successful in this class. I don't think it would be appropriate to put them into a lower level course under those circumstances. I want to see effort out of them. So I made them stay through a whole year, and I made them put in the effort. It's like, no, you don't get to go to an easier class just because you want to be lazy. No, you're going to put the effort in here, and you're going to fulfill your potential. And that's what they had to do, and that's what they did. Right? And because of that, they're on track now. Right? But if I let them off the hook, they would have been on that lower track for the rest of their mathematical careers, and it would not have served them well. Right? So, freshmen in high school, how do you make them see that as anything other than a punishment? Oh, you're going to make me stay here. But it's for their own good. When they're seniors, it's a different story. They'll have a different viewpoint. Right? But it's this sort of analysis that kind of leads that way of thinking. Right? So to answer the question, test the claim that there's no association between row variable and the column variable. All right? So I'm going to be lazy again. I just got to go back a little further to be lazy. I put in a lot of effort to be lazy, so you just got to bear with me here. There is sufficient evidence to reject the claim that there is no association between passing and failing. And again, streamline it. Between passing and failing and course. So no association between passing and failing and type of course. At the 0.05 significance level, if I'm not mistaken. Come on. Get over there. Get over. And then I lost it. I just want to expand the length. There it is. Oh, now, okay. Yeah, now. I guess I'll just let that happen. All right, well, it kind of worked out. And it was 0.05, right? Okay. And again, just like the last two, if the question said to determine if there was some kind of association, we'd have to put a follow-up sentence in there. But and in this case, it would not be really inappropriate to put a follow-up sentence. Therefore, there is some association, but it's covered here. Right? It's just, it seems like we're talking in double negatives often, and so that could be kind of mind-bending. You want to kind of just double check and make sure, wait, does that make sense? But the template makes it make sense, right? So as long as you're following, reject means sufficient, you're stating what the null is, you're stating the alpha value, the logic is already set up for you, all right? Sometimes trying to reread it and make sense of it can kind of make it make less sense. But if we're saying that there is sufficient evidence to reject no association, we're rejecting no association, which means we're accepting some association. Even though that's not what the question was asking, it's something that you might want to have in mind. All right.
I could talk about the p-value on this, I don't want to kind of
The p-value?
P-value, what exactly is not,
The p-value is less than alpha. And so that's always what we're looking for. We want to determine if the p-value is going to be less than the alpha value. If it is less than the alpha value, then we reject the null hypothesis. And 0.005 is definitely less than 0.05.